Welcome everyone. I think we should have a quick start because there's a lot to cover. And if you want to make it in 60 minutes and you don't want me to talk too fast as I usually do, we better start on time. So welcome to the Extreme Performance series to Performance Best Practices. My name is VIN2677BE. I work in support in Premier Services in Cork, Ireland. Have been there for 10 years. And what I do is performance. So let's talk about the best practices. We do not talk about anything that needs the disclaimer, but it's in there anyway. I'm pretty sure you've seen it before, you know what's in there. And if my tongue slips on something, you read it, and I'm in no way liable. So what we're going to talk about is CPU usage accounting, and I hear some of you, oh, not again. But we're going to do it as often as we need to until I don't get questions anymore. So CPU usage accounting is a mandatory part of the program. And probably also some of the material that you've already seen if you've been here the last few years. And I do see a few familiar faces. So try to power through this with me. It's a little bit shortened. And then we talk about latency sensitivity and what it is and what it doesn't do and when you need it and when you don't need it. And then we're going to dive a little bit into active memory because of recent relevance. All right, to kick it right off. So the performance best practices document here in the 6-7 iteration. It was released in early August, and who here has read it? 3, 4, 5, all right. Who here knows it exists? Yeah. So it's actually not that big, right? Last year I made a joke, you saw the file size and then you decided not to read it, but it's actually only 1.3 megabytes because there's no screenshots in it and no pictures whatsoever, which to be honest makes it harder to read. Wink, wink. So it is 88 pages and it has 4 chapters and totally it has 514 best practices. I didn't count them. I just counted the little bullet points, and that actually is not too much. I read it in 2 to 3 hours on my way to Las Vegas for VMworld there, and you can see that here on my DX Kindle, and in the background you see a 747-400 from British Airways. Probably the same model I flew into America the first time 17 years ago. It was interesting, but it is definitely readable and there's tons in there. So there's much in it. And this was way hotter when I was in Las Vegas. 2 months later it's not as cool anymore, but back then it was hilarious. But there's lots to cover here, and we could be here all day if we would talk about every single performance best practice. If we would go through everything here, I could just sit down and read it to you, and it would be pretty boring pretty fast. Even more boring than it's going to be. No, I'm just hopefully kidding. But there is lots in here and you should read it, and if you fly home, not drive please, even if you have autopilot, if you have a flight or a train home, have a go at it. It really doesn't take too long. But we're going to focus on specific topics. If you want to look for application specific tuning for the performance best practice guide, the links are there. If you want to take a quick picture, or I'm pretty sure you should get PDF exports at the end of this. It happened last year. I'm not sure whether it will happen again. You never really know. So, CPU usage accounting. Again, a few of you have been through this with me before, so a little bit of repetition might not be too bad. If we want to account CPU usage, right, what is that, right? We want to put a number against something, but in what kind of states can that something be, right? If you're talking about something that runs on a CPU, like a thread, or in ESXi terms a world, what can it do? Well, it can either run or it cannot run, right? It can either be running on a CPU or it can currently at this present time not be executing anything. This not running can be split into it simply having to wait to run because there is no resource like ready or co-stop, which is a specific type of ready, or it can be idle. In case this is a guest, when the guest runs the idle thread and executes halt, we actually deschedule that. So it can be yielding, voluntary not running, or it cannot run because there are no resources, and it can be running. Now running just means run on a CPU, but there's many factors that influence the performance and the speed on a CPU. So what we need is we need a standard to normalize that against. You know how you normalize charts against one or against something specific? If you want to compare something, you need something that doesn't change, right, or that is constant. And we normalize our CPU usage counter against the nominal frequency, that is the frequency that it's printed on the CPU. It's called nominal frequency or base frequency at core speed with no interruptions. So single core speed at nominal frequency, that is our baseline. And against that, we create a counter called usage. Now, in an ideal world, usage is exactly the same as running, right? If you run something, it should be running at full core speed at the full frequency, right? Now, sadly, that doesn't always work. There's many things that could impact usage while not impact running. So this thread, this world, this vCPU can be running on a physical CPU and it can be impacted by overlap. It's basically interrupt. So whenever an interrupt comes in, the vCPU gets interrupted, has to run the interrupt service routine, bottom halves, and then, well, not the bottom halves, go back to the vCPU. The easiest way to explain this is when you're sitting in front of your computer and you have your noise cancelling headphones on, which is like the international language for do not disturb me, which funnily enough no one really cares about. So if you sit in front of your computer and someone comes to you and taps on your shoulder, the time it takes you to take off the headphones and say go away and put them back on, that's overlap. HD busy is the cost or the impact of hyperthreading. All right, I'm going to go into hyperthreading a little bit later, but it's basically if two things run at the same time on the same core, both of them will not run as fast as they would if there was nothing else on the hypertwin. And there's a certain cost, and that is also deducted from usage. And then there's frequency. I mean, we know that the frequency of a CPU should not be the main decision of buying a CPU, but everything else being equal, the frequency on the same CPU obviously is the most important criteria, everything else being equal. So this overlap HD busy and ready time, this involuntarily not running at full nominal frequency on a core is also called stolen time. Not steal time on Linux, stolen time. There's a difference there. Now, this stolen time is also called latency or contention in VROPs, or latency is latency CPU. And yes, okay. So hyperthreading. There is a few misconceptions that I always like to go through when people talk about hyperthreading, and that is what happens when you enable it and what doesn't happen. So what some people think is that as soon as you switch click the switch, you jump from one big physical core at full performance and full frequency, and it creates a full physical core and a tiny little 25% improvement logical core. So you have a physical core and the logical core next to each other, and that anything that runs on the physical core is fast and everything that runs on the logical core is slow. That's not how it works. What I also hear is that as soon as you enable it, it actually creates half of the full capacity. So if you have one single core that can have 100% throughput, assuming 25% hyperthreading benefit, you divide those two and now you have two logical CPUs that can run at 62.5% of the physical one. Basically even split. So as soon as you disable it, you immediately have an impact because something will run slower. That is also not the case. How it actually works, and I'm sorry if you've seen this before, but I love it. Not because it's ambiguous, that in English it might just see beer, but in German it still says beer after all, even though you can't really see it. But it's actually the best representation because you have things that individually at their connection could be drained a lot faster than two of the things together at the same time. Overall, you still have more throughput down here, right? But the work that gets done, similar to the liquid going down, is actually slower. So you have an individual performance impact, but you have aggregate performance throughput, right? So that is the main story for hyperthreading. Things have to be running on the same core at the same time, and what the ESXi scheduler does, well, it tries to avoid that until it can no longer avoid it, because we want threads to progress at core rates and not at reduced rates. So how that works, if we imagine that these two 100% CPU usage comes in and they come into a funnel that is 25% bigger, ultimately the actual usage that gets reflected on the vCPU worlds if they run on the same core must then be half of 125, right? Now this 25% figure is nothing that we came up with. It's actually something that Intel advised, and also, funnily enough, what we can test on many workloads. But on ESXi, this is in no way a representation of what the actual impact is. It is simply a constant that can be defined, right? This is the assumed impact. We need that for scheduling. You can never really measure what the real impact is because that heavily depends on workload. So ESXi picks a figure that is probably for most workloads accurate. So again, hyperthreading has individual impact when two threads run on the same hypertwin. All right, so here I included a picture, you might remember the C# client, of utilization and usage. The reason why it's a C# client is because we at VMware have a secret client that works in 6.7. No, I'm just kidding. This is simply an old screenshot, and sorry if that was not a good joke or tasteless joke for some of you. It's really H5C everywhere, and I love that client. And if I would have rather have a H5C client screenshot, but this was the best one I can find. And what you see here is utilization and usage. You see usage here, that's the CPU usage, right? Again, we account everything against a single core at nominal frequency, right? So utilization is similar to your CPU usage counter. Basically, it's just whether something is running, right? Whether something is scheduled, but it doesn't really tell you at what rate it progresses. It just tells you whether it's idle or running. Usage is here already at nearly 100% by the time we start using hyperthreading effectively or more effectively, right? So basically, hyperthreading is used at a point, eliminating certain topology and VM sizes, is used at a point where the host is nearly redlining from your standard UI tools. So again, hyperthreading is usually used at the end of the scale. So L1TF, some people still remember it. I mean, the news cycle is fast. Not as fast as CNN, but still. Are we talking about L1TF? No. And the reason is because I'm not a security expert. And there's someone else talking about it at a different pay grade. And I'm not going to say anything. And that someone is Richard Brunner, and he's going to talk about vSphere mitigations. And he is up on Thursday. If you haven't seen the recordings in Las Vegas, go there and he'll tell you everything you want to know and even more that you never wanted to hear. It's a very good session. I can really recommend it. Power management. Again, you've been through this with me before, but I want to talk about it because it is still the most common performance impact that our customers have, and we have to limit it every single time when a performance issue comes in because it's just so unpredictable. So, but this power management, right, is a massive umbrella term, and it contains so much things, right? So many different settings and functions and technologies that it's really hard to just call it power management, or I turn power management off or on. There's a lot more behind that. I'm not going to talk about all those details here. What I want to talk about is the two things that are actually relevant for ESXi, or for something that ESXi can control, and for most of you, and that is P states, also known as power regulator, CPU power management, and P states is a voltage frequency state. So basically the frequency of a CPU, and it's predefined in certain steps depending on the CPU. And this only applies when something is running. Deep C states are only relevant when something is idling, right? So when the idle thread is running, we turn off certain components on the CPU. We idle, and then the CPU turns off certain components, flashes lower order caches into higher order caches to conserve power. So P states is what interests us because that usually has the biggest impact on performance that you don't want, right? So P states has the impact that when you're not running at the frequency at nominal frequency, or when you're running at half the frequency, if you want to finish something, that's obviously not good. Deep C states actually help in performance, and we're going to go into why a little bit later. Now, here we have the different settings on an HP, and if you want to take a quick picture, if you have HP, then do it now because I'm going to switch over to Dell. Yes, I have a favorite. Now, so I can go back later if you want, plus if it's in the recording you can just pause it. But here are the different performance profiles, right? So when we talk about power management, that means we configure a profile that sets certain other underlying settings, like all of these words that were under the umbrella. And what happens is that at the default setting, the P state, the frequency, can be controlled by the BIOS, but it usually overemphasizes power conservation or performance, and that is not good. Now, many people say I just go to high performance, and that's also fair enough, but usually what we're looking for is a custom configuration where you present deep C states to the host. Now, whether you present P states, I don't really care. I like it because it's nice to be able to configure the frequency in ESXi on the go for testing, for eliminating of certain things, or simply in power outages. So we recommend a custom configuration, which is also covered in the performance best practices. So these two settings, P states and deep C states, are the only ones that ESXi actually recognizes. When you look at the power management screen within ESXi, those are the technologies that it detects. And what it detects is the state of the presentation, like whether you presented the control of P states or S controlled to the ESXi, or whether it can control going into deeper C states. So I have this playing field, right, on where you are depending on how your BIOS configuration is. Who here knows what their BIOS power management policy is? All right, I was Well, and this is life-changing, not a repetition. That's awesome. So I have this playing field on where you are. If you don't know what you have configured, then please, 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 if you don't take anything else away but this, if you want to leave after this and just walk out, then remember to check your power management policy setting. You wouldn't believe how many escalations we walked through where we discover after 2 weeks that the critical component in the SDDC was an SQL server that ran on a host where the power management policy was configured to dynamic and it ran at half the frequency and it was holding up the whole shebang. So please make that your one priority when you go home and check. Now, you're a little bit better off if you run dynamic on Haswell. The reason for that is that it has per core P states, meaning that there's multiple voltage regulators going into multiple voltage regulators going into the socket and one per core, meaning the BIOS can control the P states of the core individually. Before Haswell, it affected all cores the same because there was only one voltage plane. So meaning that pre-Haswell, the cores were running mostly at 50%, where on Haswell it's a little bit better, but it's not fully gone. Now you might say, why? I don't want this dynamic, I want full performance. So yeah, you configure the BIOS for a maximum or high performance or low latency setting. And that's perfectly fine. I'd say this is a good step that you can make, and if you want it simple, if you want it easy, then that's definitely something you can do. But there is something in my opinion that is better, and that is configuring a custom profile so that ESXi can have those deep sea states. Why? Well, first of all, you can conserve power. I mean, our planet is a little bit important, isn't it? But I'm not going to make this a sustainability session, at least not this year. But it's conserving power but also maximizing performance. Why does it maximize performance? Again, the P states and the deep sea states are the only thing that ESXi sees, right? And well, a little bit more, but let's just keep that on the outside. We see P states and C states, and if you look in the HTML5 client into the power management technology, you see those two states. That means that ESXi is in control or can control P states and C states. If you don't see either, that means that it can control it. For example, if you go into power management policy and you just see C states, that probably means that you're running on the default dynamic policy. Right? If you go back in the recording to the earlier slide with the profile settings, you could see that the P states were system controlled, but deep C states were presented. So if I only see C states there, then that's a good indicator that the policy wasn't changed, unless you configured a custom policy and only presented deep C states. Sadly, it's kind of hard to identify that just from here, but you can look at certain stats to actually make that separation. All right. So why do we want deep C states? Well, the reason is that if you have deep C states enabled and ESXi can use those to idle certain cores, that other cores will run faster. There's something called Turbo Boost, and Turbo Boost is dynamic supported overclocking. It's the microcode of the CPU that decides how fast to run. It can overclock the individual cores when they run at P0, so at max frequency, and it can give it so-called turbo bins. And a turbo bin is 100, well, depending on the front side bus, steps up, and they're dynamic. And the decision on how many turbo bins are added to your nominal frequency, right, whether you run 400 megahertz faster or 1 gigahertz faster, is depending on how many cores are in a deep C state. Now there is a certain maximum of, like, depending on the CPU type, it depends on the model, there's a certain maximum that you can reach without deep C states. If you want to get the maximum turbo boost frequency that is advertised for your CPU, you need deep C states enabled, and you need a balanced policy or a custom policy in ESXi that allows the usage. So that is, in my opinion, the optimal setting. There's a few that want it a little bit more deterministic, but I'd say for 95% of workloads, this is the way to go. Because now what you see when you're looking at use and run stats, usage is actually faster. Given that we normalize against single core nominal frequency, now that we have 1 gigahertz run 1 gigahertz faster, you see that usage goes beyond just running. All right, latency sensitivity. Anyone here is using latency sensitivity? That's more people than read the performance best practices, so that's good. So if you use it, do you know that you use it for the right reasons? And this is exactly what I want to cover. And maybe some people in here are not using it yet, but realize, hey, I actually do need to use it. Or they know when someone tells them, hey, you got to use it, you have the answer to say, no, I actually don't. This is too expensive. And we're going to go into that now. So latency sensitivity, for you who haven't seen it, this is in the Flex client, is under VM options, on the very bottom of advanced. And you have low, normal, medium, and high. Those are the 4 settings available via the flex client. And there is this little information icon here, right? And you assume that when you click that, you get all the necessary information you know on what it is and what it does. When we click on that, we're seeing this. Yeah, do not use, normal, do not use, high. Okay, that doesn't really tell us much. Plus the kerning is awful if you look at this. It's not equipped at the flex client, but luckily this is now also possible in the HTML5 client. One word, I'm not going to go into specific settings, but the low setting and the medium setting are now deprecated. And they only used to change the coalescing settings. The real heavy hitting stuff, the memory pre-allocation, the exclusive affinity of the CPUs, that only is high. So in reality, only normal and high are something that you should have considered in the past. There is actually an issue there with low, but I might not get into that depending on time. Okay, so in the HTML5 client, we now have this. So we have reduced it down to the 2 only settings that are relevant, normal and high. Oh, did someone turn off the lights because it just got dark in here? No, nothing? Okay. But gee. So this is the HTML5 client in dark mode. The dark theme is now officially supported in 6.7U1. There used to be a Chrome extension for, well, an unsupported Chrome extension for the dark theme from Clarity that you can use pre 6.7, but this one is the fully supported dark theme. And you can switch the theme here in the corner, and even action buttons are back, right? So if that is not a reason to go to 6.1 update 1, even before the next patch is out, I don't know what is. But definitely one of my favorite pieces of product that is that it's not performance related. All right, lights on, and continue where we left off. So we're back at latency sensitivity, right? And we have normal and we have high. So sadly, what many people read is not latency sensitivity as an advanced option under VM options that is fairly hidden and not on the front. They think it's just a turbo button. Does everyone remember the turbo button on 486 processors and what it did what actually clock it down to 1 megahertz when you unclicked it so it could run those old games that had to adhere to a certain frequency. So latency sensitivity is not a general turbo button, right? If you click it and your machine goes faster, that's good. But if it was something that could at no cost address any performance issue, there wouldn't be a button, it would be the default, right? So you really have to think about the use case for latency sensitivity. And the reason for that is the cost. So what is cost? Okay. We're going to go into what latency sensitivity does. It is a profile. And as a profile, it covers many different things. It covers CPU, it covers memory, and it covers network. So it makes certain changes on these 3 levels to give you the end result of making this VM more latency sensitive or more suitable for latency sensitive workloads. So what does it do on the CPU level? Well, first of all, it sets a direct affinity. And it's not the affinity we see here in the Flex client, the scheduling affinity, which is an affinity for all of the worlds of that VM. That is not it, right? Not at all. What it actually sets is a vCPU to pCPU affinity. So it's a direct affinity just for the vCPU worlds. The regular get.cpu affinity, basically all of the worlds inside of this VM scheduling group can migrate around all of the pCPUs that you have defined. Whereas the direct CPU affinity means that one vCPU only is on one pCPU and it doesn't go anywhere else. Now this setting is not supported on its own. I'm listing this here for full disclosure. If you just do it, that would not be a supported thing. Plus the outcome that you want is more likely different than what you expect. But we can talk about this after the session. So this scheduling affinity is done automatically, and it's, if you have hyperthreading enabled, only affinitizes one vCPU to one pCPU of that hypertwin, right? So you only ever use one thread on a core. Then it does exclusive affinity. Now affinity only means where you are. It doesn't mean guaranteed, you're guaranteed to be running by yourself. Affinity means where you are. If some other VMs are running, it just means that you have to wake up on that CPU even if other VMs are bogging you down. The exclusive affinity part of it is what guarantees you that nothing else runs on it, right? So this basically excludes everything. Now on a CPU level, what we see when we look at ESXtop, and I hope most of you have seen ESXtop, hands up if you have used ESXtop in the past. Oh, that's very good. See, this is the participation I want. If you have used ESXtop before, this is an expanded VM. You press E, you put in the GID, and you see all of the worlds that are under a VM in 6.7. Now you might have seen that under 6.7 we have these I/O worlds as well under the VM. But what we're looking for are the vCPUs, that scheduling part of latency sensitivity. And here we see 100% run, 0% usage. Huh, what's going on there? There is no contention there, right? Maybe you remember from 20 minutes ago where we talked about run and usage, but there is actually no stolen time here. So what happens is that we configure two things. One, we do not deschedule the VM. Descheduling means that if we pick up, actually I'm going to go into that in a second. We don't deschedule the VM and we let the VM halt in the monitor. What does that mean? That means that run is always going to be 100 because we don't deschedule the VM, and the usage is approximately what the VM is using, what you see inside the guest and task manager. So why does that happen? Well, let me talk about some of the components that we use and what happens. So we have this VM kernel that is responsible for scheduling everything, and then we have guest operating systems and their applications that run on a virtual machine monitor. And this is very extreme. It usually looks more like this, right? Most workloads run on what we call direct execution, or what is called direct execution. So any instruction that is running inside the guest is pretty much running at bare metal speed. There's only some instructions that require the virtual machine monitor or other resources like I/O to step in and do additional work on behalf of the VM. So basically, if this vCPU is running on the pCPU and it's executing instructions and everything is going fine because it's direct execution, there is no instruction in there that does anything that would change the machine state, so the virtual machine monitor doesn't have to step in. But then all of a sudden, HLT, halt. Halt is the instruction that in theory would turn off certain parts of a CPU, a C state, right? It would cause caches to be flushed, it would cause power gating. So again, it would turn off the power to certain parts of the CPU. Do you want a VM to turn off your CPU? No, right? Then you couldn't overcommit. So what happens is when you see that halt, not the first one necessarily, but when we see that halt, we deschedule the VM. We put it aside and let another VM run. So at this part, the VMM says, hey, we captured a halt instruction here, and tells the VMK, put this vCPU somewhere else, it's currently not running. And then the VM kernel decides, hey, what can I put on this vCPU now? Meaning the scheduler runs. And it could put another CPU, same VM, different VM, or another world. Or it could run ESXi own idle threads. We don't want that the guest idles, but we still have our own idle threads that execute. And if you have deep C states enabled, then maybe some other vCPUs will run quicker. So this is what happens, and this is what we disable. Now this process that you saw here of descheduling a VM when it idles is completely removed now. So this part of the wake up latency or sleep latency is completely removed because the VM is running there and it can idle inside of the monitor, and we do not move it away. So all of the associated cost with that is removed. And I was talking about hyperthreading and how it looks. Again, we promise single core throughput, right? Meaning that if we look at, this is the power view in an ESX top, if you press P. And if you look at 0 and 1 is one thread of the same core. 2 and 3 are two threads of the same core. 5 and 4 are, 8 and 9 are, and 10 and 11 are. And as you see, only one part is at 100% busy, 100% utilized, and 100% C0, so running, right? It is not idling whatsoever. So again, if you enable latency sensitivity, you block a full core for every single vCPU. If your workload is worth that, fair enough. But that's not where it stops. So this can still be broken, right? It's as much guaranteed as we can, but if you set affinities across these things, you can still break it if you want to, right? So if you overutilize NUMA node affinity, regular affinity, or even use direct affinity, even though it's not supported, you can break that. So if you have latency sensitive VMs, you want to be able to identify whether they're running correctly. So if we look at the vCPUs here, how can we identify whether they're running exclusive affinity enabled? Well, the 100% run is a pretty common giveaway, right? If they're 100% run and they're not 100% used, they're probably latency affinity exclusive. And in 6.7, there is even a setting here, column xf, x_f, where it says whether something has exclusive affinity. Now again, exclusive affinity can in theory drop out at any given point. There are certain requirements, meaning that the vCPUs can have a full core for themselves. And if that is not given for any of the cores of the VM, it drops out of exclusive affinity completely and you lose that benefit. Now, I gotta admit something. I was asked this by a customer a few days ago. And the affinity bit mask is not changed anymore for latency affinity VMs. I actually have to check whether that's intentional or a bug. So I'll get back to you on that. But if you just check the affinity bit mask in 6.5 or 6.7, you will not see that, but you will see exclusive affinity. Where you do see it is actually in a tool called ChatStats, and I just gave you an example here. We call ChatStats with the CPU graph, and we pipe that to awk because we want the first line. We are looking for VMs or resource pools in the 5th column, and then we print certain stats here. And you can copy that off if you want later, but that gives us some information about the names, the mode, and the affinity. So in ChatStats you can still see the direct affinity. You can't do that in ES6 top at this point in time. I'll figure out whether it's by intentional or not. And if it wasn't, I'm not going to tell you later. So what is the requirement? Now, for this exclusive affinity to work, the VM needs per vCPU core entitlements. Those core entitlements can be guaranteed with a CPU guarantee. So basically, if you have 4 vCPUs and every CPU you can reserve, the maximum you can reserve for every vCPU is the nominal frequency of the CPU. So if this says 24 gigahertz, that would mean 6 gigahertz per vCPU. Now that's a bigger CPU than I've ever seen, unless it's some over-tacted Pentium 4. So this is not possible. This maximum is actually referring to the group the VM is in. And that was only fixed in ESXi 6.5 and in 6.7U1. So in 6.7U1 and 6.5 you see the maximum value you can reserve. Right now, before that, if you put this in, you cannot boot the VM because you would be reserving too much for the amount of vCPUs. How do you know how much you can reserve? Well, a little bit cumbersome, but you start the VM, you look at the error message, you see how much it asks for, and then you put that in. It's pretty good. Only one more step. So this was fixed, and it can be disabled, right? So this enforcement of CPU guarantee was only introduced in 6.7, and you can remove it, but why would you? I mean, if you have a latency sensitive VM, right? Would you ever want it to drop out of that at any point in time, fail over some other incident, a runaway VM? I would say no, unless it's opportunistic. I haven't had a single use case where you want to do that, but if you have one, then please let me know. Yeah, Ken doesn't mean you should. So for memory, the memory part is straightforward, right? What it does, it wants the VM to be as jitter-free as humanly possible. So usually what happens that if in a VM you open up a program and it does an allocation of a page, it says, hey, I want this physical page. ESXi realizes, wow, we don't have any physical machine page that is back in that physical page. Let's go and get that page. So that's called a double page fault. And what happened? This takes longer than a regular page fault. So if you would measure memory access latency in a VM and outside, you would assume that it takes nearly twice as much for the first, not for any subsequent, for the first page fault to a new page. And if you want to eliminate that, what we do is we allocate everything before the VM even starts. We go ahead, we get all the pages, and we present them to the VM. So all of the allocation, the consumed, the mapped, the touched, is all going to be at the value of the memory allocation. We're guaranteeing not only a reservation, we're guaranteeing that everything is there before the VM even asks for it. And that is interesting for workloads that do not warm up their caches, right? If you have a database, that usually goes through and touches everything, and then there's no big deal, but this avoids all of that. And the settings for that, again, not really supported if you do it by yourself, but I like to show them just for being complete, and so you can play with them and test with it, but not hopefully run your production environment. But this pre-alloc pin mainman true disables remap, defrag. So basically it disables anything that could move parts of the VM, like the NUMA scheduler. You cannot migrate a VM that has everything pre-allocated because there is no remapper anymore. You cannot get that memory from one node to another. So the same thing is also required and set for 1 gigabyte pages. So if you back the VM at 1 gigabyte pages, that's new in ESXi 6.7 and hardware version 14. Fault tolerance, pass-through, vGPU, all of these settings now require pinned mainmem. Now there's something else, and that is the pre-alloc guest mem, and that disables transparent page sharing, ballooning, zipping, and enforces the full reservation, right? It basically just says you cannot enable this VM without having a full memory reservation. So what is the most common symptom if you have a latency sensitive high VM? This here. Does anyone know this heading here, virtual machine memory usage error alarm? Has anyone seen that in the past, recent past? Yeah, a few more. there's more than just this particular example, and that's why I'm talking about active memory. Now, what happens is because we use active memory for the entitlement calculation, and I'm going to go into detail what that is and why we do it, this is going to alarm you when you have latency sensitivity high, and for the other VMs that also use pre-allocation. So the memory reservation, as we see here, has always been that you need to reserve the full amount of memory or the VM wouldn't boot. You can't turn that off. That is just the requirement because pre-allocation demands that. Network. The network stuff is interesting. What we saw before was pretty much scheduling latency sensitivity. But if there's also network latency sensitivity, so it matters how fast something, once it arrives, goes to the VM, and once it is issued, goes out, there's also network latency improvements. And there's 3 steps to this, right? One, it disables LRO. LRO is large receive offload. So basically, even the software layer, even without any hardware support from the NIC, we concatenate small packets into a large packet and hand it through to the guest because it's a little bit more efficient. So basically, saving CPU cycles within the guest, meaning our stack can do it more efficient and we just hand that off. We disable that. Why? Because if you have to wait for packets before you do a big packet, before I put it in, that means the first packet arrives later than it would have if we wouldn't have done that. So that's disabled. We also disable VNIC coalescing, and I'm going to explain what that is in detail in a little bit. But basically, when something is issued on the TX thread, it goes out immediately. If something is received, we interrupt immediately. There is no delay and no concatenation. And then there's a dynamic queuing, which we also disable. NetQueue is a feature that does many things. One of it is called dynamic netqueue. And dynamic netqueue means that the hypervisor could share queues that are not very used. So if you have 8 queues, then the hypervisor could decide, hey, those 4 VMs use this one queue. And that is disabled here because we want a dedicated netqueue for that VM or for however many threads that VM is using. And that guarantees that. So this is completely disabled. And the coalescing bit is interesting because it actually causes not only better latency sensitivity, but it also increases CPU usage. And the reason for that is simple. If you have to interrupt something for every packet that comes in, right, then you have to interrupt for every single packet. If you coalesce, you wait for a while. And so you wait for 5 packets, 20 packets, 30 packets. You wait for a certain maximum time, and then you interrupt, and then you give all of the packets. So how that looks is approximately like this. Imagine you issue I/O, and in the bottom scenario, we send it, and we get a response back. In the upper examples, we wait for a while, so that we can issue them more cost effective, right? So as you see, the return on the bottom where there is no coalescing is quick. Every packet gets returned immediately. So again, latency reduction. At the top, you can see that there's less interrupts and less CPU usage spent on the overall transaction. How can you verify that? I've been through a few stats already, shed stats, mem stats, and hopefully you look at those and experiment with them. But there's also net stats. And if we look at the port number of netstats, we can actually query that here with netstats, and we see that coalescing is disabled. Just to verify that it really is off. You could also configure it for other VMs where you do not have the latency sensitive requirement and just disable the network coalescing. There are workloads that require that. I'm not going to walk you through the verification, but you can verify on VSI or with vSwitch yourself that the port have no coalescing. You're not going to get any nice error message here. I basically just said not supported because it isn't there, it wasn't created. Again, that is just verification of something that should work. But I always like to leave some breadcrumbs so you can go through it and identify why something isn't working. Now, if you want just that scheduling latency sensitivity and you don't want to deal with the extra CPU usage of latency sensitivity for the network, you want more throughput, and you want that as little cost as possible, you can turn that off. You can turn off the network part of latency sensitivity. But latency sensitivity is a per VM setting. Turning net latency awareness on basically means that you disable it for every VM running on that host. It's not a per VM setting, sadly. So if you have a host, you would have to consolidate those VMs or just run 1 or 2 VMs where that is necessary. All right, what are some common issues? Many people run latency sensitive VMs that are not latency sensitive. So the first of the issue is the overreaction. People use it that shouldn't, and they have a massive cost of CPU usage because those VMs effectively block all those CPUs. But that only happens if it's reserved. What happens if you don't reserve the CPUs of a VM that requires a full core? Well, there's not going to be any exclusive affinity. So basically, if the VM, if your host all of a sudden gets oversubscribed and you're not on 6.7 or you didn't configure full CPU reservation, you'll drop out of it again. So basically, how you can verify that is check the bits I said you earlier, the exclusive affinity bit, and that it's 100% run. But make sure that if you have a latency sensitive VM, reserve the CPU in full. So the entitled core is something that you can check. This here is a vCPU, and this here, basically you get the vCPU by looking at the ID in an expanded VM in ESXtop. And what we can see here is called entitled cores. So this is how many cores this VM is entitled to because of its reservation and because what else is going on in the system. Now if this was a VM that had 9 vCPUs, it would not run with exclusive affinity. It wouldn't be disabled. This is the maximum amount of cores it can get at this point in time. So if your vCPUs are less than this, it'll work. So this is the one setting I would check. If you think you have a full reservation, you might not have a full reservation. It might be off by a few megahertz. That can happen. And there were issues in vCenter in the past where you couldn't actually reserve the full amount, but I don't want to dwell on that because it's a little bit embarrassing. All right. So I said I don't want to dwell on that is my next point. So basically this except problem that you couldn't reserve the full CPU amount, you can only reserve about 4 or 5 megahertz below that was a rounding error, but that got addressed in 6.5 GA, and I assume no one here is running something older than 6.5 GA, right? Yeah. 5.5 is at an end of life, by the way, I'm just going to remind you. Well, end of support, sorry, not end of life. So if you use VCD, you had the option to configure latency sensitive VMs for quite a while. The problem is that the allocation models in vCloud Director actually define a guarantee that limits the overall resource pool those VMs are in. So the per VM pool has a limit, that is the amount of frequency that you define for the vCPUs times the number of vCPUs. But because I/O gets charged to a VM, that means that you cannot have a full reservation for vCPUs if there is any other work being done by SVGA worlds, MKS world, network worlds. Meaning VCD was limiting the VM, meaning exclusive affinity never really turned on. This was only recently fixed in 9.1 and 4 and older, newer, where you can now say allow CPU resources to grow beyond reserved value. Again, I don't name these things, I don't know who thinks of these names, but it doesn't tell me what it is doing. So if you run VCD and you want latency sensitive VMs, check this out, you need 9.1. And another embarrassing thing that we couldn't fix earlier than 6.7, if you have a latency sensitive VM, remember this difference between run and used, right? And how we said that is stolen time. Well, in this instance it isn't, but we calculated it that way before 6.7. So if you run a latency sensitive VM and it is idle, you might actually see contention in VROPS or latency sensitivity CPU for those VMs. They're not contended, it's just the used run difference for these VMs. Again, this got fixed in 6.7, won't be backported. So if you see that, you can ignore those VMs. They're not contended as long as they're fully reserved. So this is something that only recently bubbled up. If you use 6.5 and latency sensitivity, the VM might start up with 100% NUMA row mode memory. So what we're doing here is chat stats, and we're looking at NUMA clients, and we're looking at NUMA migrations. What you see here is about 8 megabyte local memory, and then you see about 512 megabytes remote memory. So basically it's 1% locality. Now, when you look at the number of NUMA migrations, they're all 0. So this was so what I'm doing here is again an awk, and I do a match on the second column, which is the group ID, and that was the group of the VM in question. When you pre-allocate where the VM first starts, that is where we get the memory from. So we wouldn't assume any NUMA migrations. And as we see for the lifetime of the VM, it stays 0. If you see that, sorry, you have to use NUMA node affinity. So this was only fixed in 6.7 GA, but not yet in 6.5, and we're working on that right now. So you heard it here first. Hey. So the workaround for that sadly is only to define a NUMA node affinity, which brings you in other operational issues because you kind of have to watch out where you put VMs. But if you need it, if you need latency sensitivity for 6.5 right now, use NUMA node affinity. But only do it after 6.5 U1 because there are different issues. It's complicated, all right? Cut us some slack. So no, but there are, it's such a complex of settings. And it's such a special circumstance, right, that it really shouldn't affect too many people. All right, so when should you use latency sensitivity? For most, I'd actually argue you don't really need to. I mean, there's a few specific applications. The amount of times I have spent in calls about a latency sensitive application that needed to be optimized for a latency sensitive workload, which turned out to be power management, so the CPU was frequency scaled, a memory limit that still happens, or slow storage. I only had like a handful of cases where there was an actual latency sensitivity application. I mean, odds are that some vendor will tell you it's latency sensitive when really all it needs is a full CPU memory reservation. So don't over configure, right? Test it out. And what I'm saying here is that if you need a certain latency response time of sub 10 microseconds, virtualization even with latency sensitivity set to high might not be the right solution for you. Tens of microseconds, that's good. And actually has worked pretty well since 5.5. Before that, just with a bunch of extra tuning. And it got better since. But if you have a latency sensitive application in hundreds of microseconds or even more, you might get a certain benefit, but is the cost of basically sacrificing a single core for every vCPU really worth it, right? There's a cost associated to everything, and latency sensitivities is pretty high. So, food for thought. Do you really need it? Active memory, also called touched memory now. I think we changed it because it got too confused. I got confused too often. All right, everyone knows where these screenshots were taken from. On the left hand side we have the HTML5 client, 6.7U1 action buttons, nice, huh? And on the right side we have the task manager. Now we see down here 0% memory active of 16 gigabytes. Yet over here we see 7 gigabytes consumed, 8 gigabytes free. For the last time ever, I'm going to say you, these two things are not the same. The stats are completely different. Active memory has never and will never, definitely, will represent anything that you can see inside the guest OS. It is a completely different metric. We're looking at it from two different sides. This is how memory is being used inside the guest. This is how much memory is being touched. So let me show you how we generate active. And I admit, in my personal opinion, and don't tell anyone I said this, but I don't think it should have made its way into the UI. It was meant as an entitlement metric. It was meant to estimate how busy that VM is without having any insight into the guest operating system at all. I know we all have our fancy VMware tools, and in theory we could get everything we wanted from the guest, but our assumption is that something is running which is a complete black box to us as long as it behaves according to x86 standards, right? So again, anything should run without tools, and we cannot make the assumption that we can look into the guest. Now, it is possible, and VROPS 6.7 showed that, but it is not the same, and we have to assume that we have no insight. We don't know any of this. So if we don't know what the guest is using memory for, why do we need this? And what do we do? So active is actually a heuristic, meaning we don't need tools for it, we just look at the VM. We also call it memory sampling, and one of the pre-allocation settings you saw earlier, you saw that we disabled sampling. If we disabled sampling, we don't have active anymore, meaning active is always at 100%. So how does it work? Now, over all of the VM's mapped memory, gigabytes or thousands or even millions of 4 kilobyte sized pages, let's ignore large pages for now, we unmap 100 at random. That doesn't sound like a much, but after 1 minute, we remap them. Why do we unmap them? Because we want to be able to track and access read or write. So we take 100 pages, we unmap them, and if something reads from it or writes to it, we track that. Then we remap them, and then we unmap another 100 pages. So basically that unmapping, remapping is moving over the whole address space, right? Because we do that once a minute. So we know when pages are read, when they're written to, and statistically speaking, that gets more accurate the longer it's running. So I was thinking about an analogy, and hopefully this works. If it doesn't work, let me know. But think of it as a glass table with food on it, right? You have your plates, entree, main, dessert, right? And you know what's on it, right? You know how much you've eaten from your salad, you know how much you've eaten from your whatever you eat. But the whatever's on there, you can see it. But if you look at it from the bottom, right? If you imagine ESXi has no idea what's there. It knows there are plates, but it doesn't know what kind of food is on there, right? So we're looking at it. We can see when you have a fork and knife and when it's moving, but you only know what the content is. Only the guest operating system knows what the content is. ESXi itself has no idea. All it knows is that it gave you some pages. And this is why we have active memory, because we want to know, hey, can we get rid of one of these plates because we didn't see that plate in the top corner move at all over the last 20 minutes, right? So when we do memory reclamation decisions, ballooning, swapping, and so on, we don't know what we can remove. So, or how much we can remove from the VM at all. So that's why we have active. If you look at active and consumed here for this particular VM, you see it was booted here, consumed goes up, active goes to 75%, which is the start default. So active will always go to 70% of the configured memory, and then it will go down, right? Whereas consumed goes up. So now you have a VM that's consuming lots of physical memory that is not very active. Usually you see that activity spikes correlate with consumption spikes, but you see that active goes down again, but consumed stays up. We do not reclaim memory unless there is contention. Especially with large pages, there's no transparent page sharing anymore, unless there is contention. So basically memory consumption will always grow, memory activity will be seen according to guest OS behavior. So, and then this question comes up, how do you size your VMs? How do you know your VMs are undersized or oversized? Well, you have different values. If you don't look at guest values, right? Everyone here, maybe some people of you have VROPs or VROPs pre 6.7. How do you do your capacity management? Is a 4 gigabyte VM, does it really need 4 gigabyte? Does it only need 500? So what do you look at? Do you look at active? Do you look at consumed? Active is at the lower end of how much memory the VM would need. And you saw this Windows VM there with 0% active. You probably don't want to give that VM 0% memory. So active is not fully truthful in regards to how much memory you actually need. But then consumed is on the other far end of the spectrum. Whatever you assign to a VM, if it's not contended for resources, will be consumed at some point in the future, right? So maybe that's a little bit too much. So you go in the middle. But where in the middle? What is the right amount of memory that you need to assign to a VM? Are you going to go a little bit closer to consumed? Are you going to go a little bit closer to active? And to be frank, that depends on your risk level. But it's not an easily answered question. Because to understand what the guest needs, you actually, or to understand what it fully needs, you need to look at in-guest stats. So let's just draw it out as a colorful line of potential risk. If you size your VMs and if you give a VM 4 gigabytes, if you make your model based on that, then yes, right? Unless some application needs more, 4 gigabytes is the maximum you can give it, there is zero risk associated. The further you walk down that line, the further you get to active, there's more risk that maybe that size is too small for what the guest actually needs. Again, we're just talking about ESXi visible metrics. And to be honest, active is not all the way down there. That screenshot I showed you was just before the HTML5 client could refresh, so it wasn't 0, it was actually on 10 or 15%. So active is closer to here, but it has still, you cannot just size your VM to what you see in active, right? Because usually there is memory that is not active, but the VM will be highly annoyed, or the application, if that memory can't be faulted in quick enough. So active, more risk, consumed, very little risk. So where do you go in that line? Now again, in Windows here, for example, you see 8 gigabytes are still available, right? So would you say that in theory, if that is the amount of memory that's always available, you can deduct that the next time you resize the VM? Well, obviously you cannot look at a point in time snapshot. You look at trends, you look at whether there's a peak, and then you size for that plus maybe a buffer. But what is in there? Why is it active, and why is it used here, and why is it consumed on ESXi? Because this available memory has actually been touched in the past. All we know is the plate it touched, right? We saw that the page moved, we gave the VM a page, and we never reclaimed it, right? We don't go out there and reclaim the pages that are free and 0. Now back in the day with transparent page sharing, before everything was backed by large pages, those 0 pages, for example, would be shared and shared saved. But that isn't happening with large page backing, and that's a completely different topic that we can go into at some point in the future if you want. But all of this has been touched in the past, meaning it's owned, but it doesn't really contain anything useful for that guest, but it is still consumed. So in theory, that could be gotten rid of with minimal impact, specifically standby and so file cache. Active, really bad that this has the same name. So this is actually the actual resident memory in Windows itself, 8 gigabytes, right? And active and hour active are not the same. I know it's the same name, but I can only stress that it's completely different things. It's looking at two different sides of the same coin, so to say. So what do you size for? Well, what you want to size for is then some sort of guest working set. If you always have 8 gigabytes free in that VM, then it probably doesn't need that 8 gigabytes, right? Unless in emergencies, but again, there is that buffer. So guest working set is the pretty optimum value. Now, the chances, and this is why I'm talking about risk here, chances are that if you have an opportunistic application, right, that the guest working set consumes everything. If you have a database, that is not just going to say, you know what, I only take half the memory because I don't need it. No, said no database ever. So the guest working set can always be too much. You always have active to say, you know what, maybe I configure less memory for the database and it would run just as fine. And that's possible. But if you want risk-aware sizing, you need in-guest stats. And activity as a guide, right? Saying, you know what, this VM might be consuming much, but we have a inkling that it actually doesn't need that much. Or maybe it does, who knows. But it gets us a lot closer to efficiency than we were before. Because the guest working set size will never underreport. It will never be less than active, right? There could be a statistical, it could be a possibility, but guest working set will never be lower than that. So that is the best point to be relatively risk aware for the sizing of your VMs. And I got to say, VROPS, it had to grow on me because I wanted a tool that I can use immediately and not invest 100 hours to make work. But with 6.7 and 7.0, I have to say I'm actually starting to be a fan of the tool. It was always good before, but it just required so much preparation work that was very hard to just get started. But that is pretty much addressed. Also, let me go back here. In VROP 6.7, we now have, it now utilizes in-guest memory stats. So we actually implemented the VMware tools guest stats in 6.0 update 1. So if you have tools and you run on 6.0 U1 host, VROPS can actually query the guest stats, so memory consumed, memory available, standby list size, and so on. And it actually takes these in-guest memory decisions and does your capacity planning based on that. So again, we're actually going in a direction where this is highly, highly useful. I don't want to chill for it, right? I mean, it's a separate license, but I actually am very happy where this is going. Now, the one caveat I would like to say is that you should be on the most up-to-date tools possible. I think there's still a little kinks in how we actually get the stats and how they're reported and what they tell us. So we're getting there, but you might need to update your tools. And if that's not a good reason, I don't know what is. So let's talk about active memory and the alarm I showed you before for latency sensitive VMs. Now, latency sensitive VMs are not the only VMs where you see that alarm. Does anyone remember this KB article? No? Okay, a few people. How was it written? Well? Not well? Never mind. In any case, the problem here was actually in 6.5 that when you have a VM that is fairly small, we made some changes in the large page promotion pass. Basically, activity would go up, but it would never go down. And that was a real issue, right? You saw the memory alarm, activity went up. It never actually was that active, and it just stayed there. We fixed that with the next patch, or I think with update 1. Then there is this other KB here. You see the memory alarm for specific types of VMs, and I assume a few more people have seen this, right? And we basically tell you to disable the alarm. Now the reason is because PCI pass-through, fault tolerance, latency sensitivity, they all have pre-allocation, meaning it deactivates sampling. And in 6.7, that also affects PCI fault tolerance and vGPU. Now, some of you have said that you don't like the actual workaround of disabling the alarm, but I'm going to ask you honestly, did this memory alarm ever once notify, ring up, and there was a real issue behind that? Not a single hand. There was actually one guy in Las Vegas who raised his arm, but he ran away before I could get to him. So the point is, it was intended as an entitlement metric, right? We wanted to know what we can potentially recover based on having no visibility into the guest, and then all of a sudden we create alarms for it, we plaster it on the UI, and people think it is the same as in-guest stats. Mea culpa, a little bit our fault. What will happen is that this alarm will most likely just be disabled by default, because really it doesn't quite provide the benefit it should. With that being said, there is more performance at VMworld, so there's a few more sessions that you can go to. And there is performance labs. And wow, on time. Don't forget to fill out your survey. It tells us what you want to hear and what you don't want to hear, and whether you want better jokes or worse jokes. At least a chuckle. But thank you so much for everything, and if you have questions, there's 2 minutes here, and I don't know whether we just go to the front, everyone, and then we'll do questions outside, okay? Awesome, thanks guys.